Okay, here we go with the next unit. This is Unit 2 notes, and we're going to start what we call one-dimensional motion. Okay, we're going to start with a few equations that we're going to use here with this unit. And then at the end of this unit, we're going to get those equations that we start off with, and then we're going to combine them into new equations that we can use. They're pretty awesome. With this information, you're able to figure out a lot of stuff without having all the parts needed. Okay, but let's start off with the basics of one-dimensional motion. Hopefully you've got your notes ready. Again, they're printed out. I'm going to video this because just in case if you miss something, you can always go back. If you feel like you got it when we talk with each other during class, then perfect. No need to watch it at all. From here on out, you're pretty much going to need your calculator with you in class. Every class that we have, you're going to need it on your quizzes and on your test as well. Okay, so a regular 4-function calculator is really not going to do you good later on. You're pretty much going to need some type of graphing calculator, something that you can do sine, cosine later on. Make sure that you have a square and square root button as well, and exponents, okay? So let me go ahead and move this to the side, and I'll have that here when I need it in just a moment. Move my ruler to the side, and here's our notes. Now, before we start with anything regarding our notes, please make sure you put your name at the top. Okay. Also, I would like to go ahead and start off with the actual dates that we have here. So I'm going to put them over here on the side. The quiz for this unit, if you're a Monday, Wednesday person, versus if you're a Tuesday, Thursday person. Okay, so let me go ahead and I'm going to put on here quiz. And if you're a Monday, Wednesday person, the quiz date is going to be on 9/21. If you're a Tuesday, Thursday person, your quiz is going to be on 9/22. For your test, Monday, Wednesday students, your test is going to be on 9/25. Next one here, your test for Tuesday, Thursday is also going to be on 9/25. That's actually going to be a Friday. Let me pause there. This last unit, we had some mishaps. One reason was because some of us were not sure or did not realize that just because you have a 2 o'clock class time with us on Monday, Wednesday, does not mean that your Friday is going to be 2 o'clock as well. Okay? Please make sure you double check, have some kind of planner, something, put it into your phone, I don't know, but something so that way you know when your class time is coming up, okay? So please make sure you know that. Also, on our test dates, I don't have anything in Teams. And the reason for that is because I do not want to take away the time from your testing. I want you to go straight into Blackboard and start your test, okay? So let's start with our notes. Unit 2 notes. Alrighty. So Unit 2 notes. A couple of things first we need to know, it says. A couple of facts when talking about physics. One-dimensional motion is motion moving in a straight line or path. Whether you're moving side to side or whether you're moving up and down, it's going to be either up and down or side to side, one-dimensional. The next unit, we're going to talk about you moving to the right and then moving up. That's two-dimensional motion, okay? So the next part here that we need to know is in physics, all quantities, and that word quantities means numbers, can be categorized into 2 groups. So kind of like biology class. In biology class, you categorized everything into the abiotic or biotic, right? Non-living or living. In physics, we group everything into what we call a scalar or a vector. Everything in physics is a scalar or a vector. Now, a scalar, let's look at that definition. A scalar is a quantity, remember, number, of measurement that actually has what we call magnitude only. So an example would be mass, the number of students, weight. So let me go ahead and throw out a few examples. 17 students. Shoe size 6.5. 122 pounds. 17 years old. All of those are what we call magnitude only. The word magnitude, for those of us who not sure about that word magnitude means a number, a value. Okay? Now, a vector in physics is a quantity of measurement that actually has magnitude and direction. Okay? So again, the word magnitude means number. The word magnitude also, another word for it could be a number or amount, a value, an amount. Okay? I use that word magnitude quite often, so making sure we know what that word means. So for an example, some vectors in physics would be displacement, acceleration, velocity, and there's a lot more, okay? Motion. It says here though, define or the definition of motion is any movement or change in position. Okay, how do I know that motion occurred? How do I know that that object really moved? Well, because there was a change in position. That's how I know that motion occurred. Now, frame of reference. We use this in physics because a frame of reference is going to help determine if motion is occurring or not. So, frame of reference says here, how do we know that an object really is moving? When an object changes position with, let me see it, respect to its reference point. In physics, we call this the background. Oops. So the reference point would be the background. It says here, think about old school Mario game. Okay, like the original Nintendo Mario games. If an object's moving, if an object is in motion, an object is in motion if it is moving against some background and stays the same. So what they're trying to say there is, if you go back and recall old school like Mario or Nintendo games, it really was that object was just there standing or bouncing or jumping, but the background against it was moving. Okay, because that background moved, then that means that even though to us, when we looked at it, it was like it was just there moving, like it looked like it was running or walking or jumping, but the background was moving. And so that background gave reference or was a reference point that my object was moving versus it just staying in the same position. A stationary background is called a frame of reference. Okay, and those stationary backgrounds are important to us. Those are our frame of reference. How do I know that it moved? How do I know that when I walk out of the classroom or a teacher walks out and leaves the classroom that the students are still there staying in their desk or not moving? How do I know? Because the frame of reference would be a stationary background, which would be their desk. So if their desk are a non-living object that's not moving, and I leave and I come back into the classroom and I see that you're still not moved or you're still at your desk, then the frame of reference was the desk, you didn't move. But if I use the frame of reference or the background as the desk and I leave the classroom and I come back and all of a sudden I see everybody crowded around one area, then all those students moved because due to the frame of reference, which was the background or the desk, they were not at that same position anymore. That means that motion did occur. Okay? Next part here. Determining if an object is moving depends on what you consider their background. You determine what the background is. Okay? Or, here's the other word, frame of reference to be. So that example that I just said with the students and the desk, I determined that the background or the frame of reference was the desk. Somebody else can choose something else to be the frame of reference. They can say the chalkboard or the backpacks on the tables. I don't know. But you determine what the background or frame of reference is. And knowing this information is important so that way we know that motion did or did not occur in physics. Next part here. It says the Earth is moving around the sun at a rate of about 18 miles per hour and is spinning about its axis of about 1,000 miles per hour. Okay? So let's stop for a moment and let's talk about this. We know that we sit here on planet Earth, and this Earth itself is rotating around the axis over and over and over again. And not only is it going around the axis, but it's also rotating all around, right? It's going to go all the way around 365 days. Another 365 days. And this rotation right here occurs in 24 hours. Now, this is something that we know. I mean, we're not like taking spaceships out of our atmosphere and we're able to see it and view it from the outside. But we do know that this does occur. Our Earth is spinning around the axis, and then it rotates all the way around the sun, 365 days for us, for 1 year. The next question is, if you, for an example, are moving this fast around the axis, around the sun, and then moving this fast around the axis, well then, why don't we feel like we're moving that fast? As you sit here and you're taking your notes, do you feel dizzy? Do you feel like you're spinning around the axis of the Earth as well as at the same time going around the sun 365 days? So you're spinning like this as you go around. Why don't you feel like you're moving that fast? I mean, maybe you do, I don't know. But me personally, I mean, I don't feel like I'm traveling that fast, like I'm hauling butt around the sun. Okay? Now, there's a reason for that. We don't feel like we're moving that fast because our background, and what's that other word instead of background? Frame of reference, is what? As you sit there and you're taking your notes, I don't know, you might be at the kitchen table, you might be at your desk in your room, you might be sitting on your bed. But your background is going to be what you right now determine. So at this moment, please determine what's your background. Is your background your bedroom? Is your background your desk? Is the background the table at the kitchen? What is the background? And as you're traveling around the Earth's axis, as well as spinning around the sun, your background is doing what? It's not moving. Right? Look at your bed. Look at your desk. Look at your kitchen table. Is it moving compared to you at this moment? No, it's not moving. It's not moving. Or some of you are already thinking a little bit differently. What else? What's the other thing? If some of us are like, you know what? I'm sitting here at my bed doing my notes and my bed is not moving. Or some of us are thinking a little differently. And that's what I love physics, because some of us think a little differently and we see those answers or those ideas or suggestions in a different point of view. And I love that. Not only is it not moving, or we can say that our background, which could be your table, your desk, your bed, is moving at the same speed as you, right? Not only are you moving around the axis of the earth and around the sun 365 days a year, but your bed, your kitchen table, your desk, your computer, your whatever, which is your background, is also moving at the same speed as you. So when you look at it right now, so look at your background, whatever you determine your background to be, is it moving in reference to you? No. But are you in your background moving, or your reference point moving at the same speed in reference to the earth or in reference to our solar system? Yes, y'all are both moving at the same time. But in reference to you, it is not moving. Okay? Next part here, it says, if you're driving down the highway now with your family and your mom tells you to stop moving, can you do it? What do? Do you backtalk her? Do you tell her, zip it? No, probably not, right? Last thing you want to do is get hit at this moment. All right. What do you tell her? How can you tell her no? Can you tell her no without getting in trouble? I'm not sure, right? But if she tells you stop moving or be still or sit still as you're traveling down the highway, how can you tell her no? Well, that's what I do like about physics, because we can go ahead and slide that in. So you tell her, bleep, no. Mom, no. Or dad, no. Or heck, no. Now, first thing, before you tell them that, you make sure that they know that you're about to back this up, okay? And that's what I love about physics, is that when we tell someone no, we're about to back that information or back that word up, that answer up, with the information that we know. So we're going to go ahead and tell them, heck no, because my frame of reference is the road. And when you compare yourself to the road, you are nonstop moving. You can't stop moving. You can't help it. In reference to the road, or in reference to the trees on the side of the road, or in reference to the other cars next to you, no, I can't stop moving. So don't ask me to be still, right? So make sure you back that up, that no up, with some physics behind it, okay? If you don't, you're taking it at your own risk, okay? But if your mom or dad or whoever throws back a little bit physics to you and says, well, I was referring to your reference point of being your car seat. Well, at that point, in reference to your car seat that you're sitting in, all right, that seat in the car, then yes, you could be still, okay? So I love how physics can back it up. Let's go ahead and get to the next part. The word is displacement now. We're about to start hitting a lot of vocabulary words. There's some vocabulary words like vector and scalar over here that you have never heard before. I'm sure you heard of motion, frame of reference. You probably heard it but thought of it in a different way. Okay. The word displacement and the word distance. I know you've heard those words before, but in physics, the word displacement and distance means two different things. Okay? Also, for an example, in physics, the word weight and mass are two different things. Okay? Just kind of like accuracy and precision do not mean the same thing. In physics, I want you to use the words correctly. So let's go ahead and get to the next word, displacement. It says here that displacement, as an object moves from one position to another, the length of the straight line drawn from its initial, because I'm giving you the definition, position to the object's final position is the definition for displacement. One more time. Displacement is, as an object moves from one position to another, it is a straight line from its initial or starting point to its final point or stopping point. Okay? The initial position is going to be the starting point. Here's another word that we use in physics. Home. And we don't legit mean like, oh, your home, your house that you live in, you sleep at. Okay? We mean that that's your home position. That's where you're starting at. Okay? Your final position is going to be the ending point. Or, here's another word, rest. You're going to hear that word a lot often. Rest, or your resting position, or your resting point. Now, displacement, even though that's a word that you've heard before, more than likely, it actually has an equation. Okay? The equation for displacement equals final position minus initial position. And for the whole school year, let me let you know now that when we do write our equations down, I like to write it out by the words first, because this is really our first equation. And then I like to go ahead and actually give it to you in the short form using our letters that we're going to use. So displacement is going to be a delta x, and this actually is a lowercase x. Remember what I told you about alphabets. They're either lowercase or uppercase. This is a lowercase x. This is called a delta. Hopefully you've seen it before in math class. Yes, you might say it's just a triangle. But a delta, okay, which is a triangle, stands for final minus initial. I don't care if we're talking about displacement. Let's go back and recall chemistry last year. You had delta T, right? Because you were trying to find the change in temperature of your object. And in math class, when you use the word change or change in, what does that mean? That means subtraction is going to occur. So it's delta x equals x sub, which is a little f, minus x sub I. Okay, so that's the equation for displacement. Hopefully you've already printed out your formula chart, right? Use that formula chart every single time you're going to take your quizzes and tests, because they're going to be important for you. Alrighty? At this moment, you've got your notes to help you. You've got your formula chart to help you. If we do get to come back to class, let me give you a warning, because I know I've said it before. I'm going to say it again. When you're in class with me, you don't have your notes with you. You don't have your homeworks with you. You don't have your smartwatch on you. You don't have your cell phone on you. You don't have any other devices on you other than your calculator next to you, right? And you use my formula chart, which is a blank, empty one that's not going to have writing all over it. Just throwing it out there. For those of you who are using everything right now at home, which I understand because you're at home, the moment you get to come back to class with me, you might have a rude awakening. So maybe you practice like you're in the game, right? Because when you come back with me in class, you're going to be in the game with none of that with you. Well, let's keep going. Next part here, towards the bottom. It says here, delta, right, which is the triangle, is a Greek letter that means change in. So the delta x means a change in the x. It means a change in x. And a lowercase x in physics means displacement. Also, though, a lowercase x can mean position, movement, distance. So the lowercase x has a few things it can stand for, okay? It stands for a few different things. The next part here, displacement is not always equal to the total distance traveled. I make sure I tell the students every single year that this is super important. This is so true. But yet every single year I always got students who get this question wrong on the test. Here we go. So displacement is not always equal to the total distance traveled. So let's go ahead and look at an example. The example is going to be this lizard over here. For an example, a lizard runs up a tree from 20 centimeter marker parentheses initial position. Now I'm starting off and with parentheses telling you that that's the initial position. Later on, I'm not going to tell you that. If this is what they tell us that my lizard is at, then this is going to be my starting or my, what's the other word? Home position. Okay, so this is my initial position or my X sub I. Okay, to travel to the 80 centimeter marker, which is the final position, but they said number 1. If they're telling me a number 1, then that means that it's going to move again to number 2 and again and again. What is the lizard's displacement at this moment? So it's a little difficult to see. I don't know if you can see over here. You've got this lizard. And believe it or not, I have pictures in your notes to kind of just help jog your memory or just in reference to things. So over here, they gave you the initial position. Okay? And why did they give it to you in the Y? They gave you Y sub I. They gave you the Y sub I instead of using an X sub I because my lizard's going to move up and down. I guess like in math class, right? You've got your graph and you've got your Y-axis that's going to move up and down, and you have your X-axis that's side to side. Same thing in physics. What you learned in math is going to carry over here. So you can call it X sub I, you can call it Y sub I, but the Y just means that it's moving up and down on the Y-axis. So here is my start, and I'm going to come over here and I'm going to put start. There we go. Now it tells me that it travels all the way to the 80 centimeter marker. Here is the 80 right here, and it told me position number 1. So I'm going to come over here, and I'm going to call this number 1. That's the stop point number 1. Well, they asked me, what is the lizard's displacement? Well, let's go back. If we want to, mathematically, we can say delta x equals x sub f minus x sub I, or I can say 80 minus 20 equals 60 centimeters. Okay, so now you see how I got that answer, 60 centimeters. I use the equation x sub f minus x sub I equals 80 minus 20, which is 60 centimeters. We all agree with that? If not, this is the time where you go ahead and start making some little notes, highlight it, get those little tabs and stick them, because when we meet with each other, you need to stop me and ask me. This I'm shy business has to cut it out now, because when you're shy and you don't ask, then that's your own education that you're putting on the line. Okay? Please don't do that. Now, I'm going to just pull this down a little bit because we're going to still use that information from the lizard. It says here, after making it to the 80 centimeter marker, now the lizard then retreats down the tree to the 50 centimeter marker, which is position number 2. So it stops here. It turns around to the, let's see, where is it at? 50. Here's 80. Here's 50. So it goes to here, which is number 2. Okay, let me let you know now. I have a little drawing or a little picture here, but we do a lot of drawing in physics. So don't give me, oh, I'm not a good drawer. I don't care. Look at my pictures. They're going to be pretty bad. I do a lot of stick figures. I'm a visual person. I need to see it. Now, at position location 2, what is the lizard's displacement after he retreats is what they're asking. Okay, well, not a problem. At this location, I'm looking at the lizard and he ran down the tree, which is okay. Not a problem, lizard. Maybe something scared him off. I don't know. But when he ran down the tree, his new location, or new, let me go this way. Delta x equals x sub f minus x sub I. Or I can say 50 centimeters minus 20 centimeters equals 30 centimeters. And that is his new displacement afterwards. Okay? Now, if the lizard was to return to the starting position, what would its displacement be then? So now he's going to go ahead and he keeps going back down over here, and I'm going to call this number 3. Here's where he started. He went all the way up, turned around, came back to here, stopped for a moment, and came back down, slash, end. He ended where he started. Hopefully we all agree with that. So in this case, I'm going to come over here and I'm going to say, again, delta x equals x sub f minus x sub I. Okay? Or, what was the final position location? 20? Minus, what was the initial position location? 20. Equals 0 centimeters. So now at this spot, his displacement, because that's what we're talking about, is 0 centimeters. Does that mean that he had a distance of 0? No. We're just talking about the word displacement. His displacement at this position is 0 because his final and his initial are the same exact location. Or, here's where he ended, here's where he started. It's at the same position. What's the difference between the ending and the starting if they're the same? What's the difference? 0. There is no difference between that. I'm going to pause for a moment. Now, let's go ahead and stop and say, well, I'm going to squeeze this in and say at this location, hopefully we can read it. There we go. What would his distance, or another word that's used is total distance, be at this position? So at location 2, if he traveled up and he traveled back down from here to here, 20 to the 30 is 10, 20, 30, 40, 50, 60, 70, 80, 90. It would be 90 centimeters would be the total distance at this position that he traveled. What was his displacement? 30. Let's come back over here at this one. At this position, his total distance, well, his displacement is 0. Does that mean that he never moved at all? No. It means that he ended up where he started off at because both those numbers subtract out to 0. But what is his total distance that he traveled? If that was the question. Let's go ahead and start from here to here. It's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and 10, 20.